So tell me where to start. RPMs. How do I find RPMs? Times 1 inch, yep. So what's that come out to be? 57.29, so 57 RPM. It's kind of slow. You got 573. Let's take a peek. Yep, 573.2, so there's a decimal point off there. So 573. Yep, somewhere. Okay, so next, what do we do with that? So 9 over 0.004 times 573. Which gives us 3.93, 3.927 minutes. So basically 4 minutes. 56 seconds. Okay. We'll allow you a couple of seconds of setup time. How's that? Okay. Now what? Well, what we're going to talk about next for today. Does anybody have any questions on all that cutting speeds and cutting times and all that stuff? Should be review for you, right?
The parentheses, why do you put like the top one that puts parentheses in the bottom one? Why do you?
You have to put the bottom in parentheses. It's not the top. Because when you, like, say you have 12 times, oh, what the heck goes on top? The top is your surface cutting speeds. Let's do 12 times 130 for your surface cutting speed. Then we're going to go over pi times, oh, so we got a 1.5 inch tool, 1.5. When we put this in the calculator, remember technically that fraction bar is an enclosing symbol. You have to do everything on top, then everything on bottom. So to be technically accurate, you should have parentheses around both the top and bottom. But the calculator will automatically do the multiply the top. Now, if there's any addition or anything up here, then you'd have to put the parentheses in. So to be more technically accurate, you should put those parentheses around that. That's just in this case, you don't have to because it's all multiplication. But on the bottom, you're going to hit divide for the fraction bar. These have to be multiplied together before you divide by them. So the parentheses are telling the calculator, yes, those are multiplied, and then you divide by the total, rather than just dividing by. Otherwise, it divides by 3.14, and then it multiplies the whole total by 1.5. Alright, so our new stuff for today, we'll see just how badly I can butcher this drawing. That's going to have to be close enough. It's going to look something like this.
2 gears.
Yes, they are gears. These are Spur Gears. Yeah, my drawing isn't horribly offensive, at least. We're dealing with these gears. There are some features that we need to define. This brown circle, I'm assuming I don't need to define what a tooth is. You guys can understand what the teeth are, right? This brown circle is what's called a pitch circle, or the circular pitch. Notice when 2 gears mesh together, their pitch circles are what we call tangent. They touch each other. Notice the pitch circle is not at the outside of the teeth or at the inside of the teeth. It's part way in between. That's considered the working contact area of the working size of the gear, basically, is that pitch circle. Of course, the diameter of that pitch circle is the pitch diameter. Now, the tooth itself has a certain depth. And that is what we call the hole depth of a gear, is the distance from that tip of the tooth into the base of the tooth. But you'll notice these don't go all the way into the base. There's a little bit here, there's a little clearance there. That's actually called the clearance. That's in the gaps between teeth. That's the distance between the tooth and the bottom of the gear, so that it doesn't bottom out. That's a little clearance so those teeth don't hit and crack. So if there's any movement, there's no problems or it doesn't bind up. So it gives us from here to here, which is the distance from the tip of one tooth to the tip of the tooth on the other gear, which is called the working depth. So the working depth of the gears. Now there is, there's an outer diameter, outer circle, inner circle, inner diameter, outer diameter. Of course, inner diameter goes to the inside of the tooth, outer diameter to the outside of the tooth. Those aren't necessarily huge deals. From the pitch circle in. So from the pitch circle in to the inside of the tooth, that is what is called the dedendum. From the pitch circle out to the outer edge of the tooth is what is called the addendum. Then there's tooth thickness, which is just the width of the tooth and stuff like that we're not going to be terribly worried about. You can find, now if you understand these pictures, if you know the outer diameter of two gears, by the way. Let's say I have two gears that are meshed together. Here's their center. And I know outer diameters, of course, are going to overlap a little bit, right? The pitch diameters, the pitch circles, yeah, pretend that's circled around it. The pitch circles are tangent, they touch each other. But the outer circles, the outer diameters will overlap because the teeth mesh together. Well, let's say that this one has an outer diameter, a full diameter of 3.8 inches. This one has a full diameter of 3.2 inches. So what's that, 1.9, 1.6? And the distance between centers is 3.35 inches. We just figured out the working depth. Because from here to here is 1.9, right? Half of the 3.8. From here to here is 1.6, half of the 3.2. If I add those together, what do we get? 3.50, right? Subtract the distance between centers, that's 150 thousandths. So it's 150 thousandths working depth on those gears. They overlap by that much here. That's what that's telling us. Everybody see what I'm saying there? Any questions? 1.9 is half the 3.8 diameter, so that's the radius of this circle. 1.6 is half the 3.2, so that's the radius of this circle. Well, those two radii overlap. So if the distance from center to center is 3.35, the total of these two is 3.50, so the difference must be the amount of the overlap. The working depth, yep. So if you open up the packet I gave you guys yesterday, it's page 247. Basically today and tomorrow are exercises in using formulas. Starting at the bottom of page 247 and going all the way down most of the page on 248, there is a table on Spur Gears and different formulas for Spur Gears. Now there's some in there you see towards the middle of page 248 where they got the asterisks by them. Any of those formulas with an asterisk, those only apply to a certain set of gears. It's a full depth involute gear. A 14.5 degree is the angle of the tooth. And that's just it's a very, very standard gear, very common gear. So those the asterisks only apply to those certain types of gears, which is what most gears are. But I should point that out. The rest of these formulas with no asterisks on, they'll apply to any spur gear, no matter how rare or how unusual it is. So the first thing we want to talk about in a gear is something called the pitch. When we're talking about standard gears, standard I mean measured with inches, the pitch is what determines whether two gears mesh together. To mesh together, two gears must have the same pitch. What the pitch does is it describes the number of teeth per inch. But it's now per inch of diameter, not just inch of circumference. Technically, the tooth spacing should be per inch of circumference, but they don't do it that way. It's per inch of diameter just to make it easier to calculate. But anyway, yeah, the pitch is N, which is the number of teeth, divided by D, which is your pitch diameter. So that's the diameter of that pitch circle. So if you have a gear that has 24 teeth and a 8-inch pitch diameter, that is a 24 over 8 or 3 pitch gear. And again, that describes the spacing between teeth, how far apart the teeth are. For two gears to mesh, they must have the exact same pitch. So if this gear here with 24 teeth and an 8-inch pitch diameter is going to be matched with another gear with a 5-inch diameter, how many teeth does it have to have? Where did I come up with the 15 teeth? 5 times 3 has to have a 3 pitch. So pitch, the way I always learned it is if you take the pitch times the pitch diameter, that gives you the required number of teeth on the gear. So if you know you're dealing with a 6-pitch system, then you take the diameter of the gear times 6, tells you how many teeth that gear has to have or it won't work in that system. Make sense? And there are all sorts of other formulas down through here. Circular pitch is PC, is circular pitch. And that is instead of taking the number of teeth, well, you're still doing the number of teeth, but instead of taking the diameter, you're taking the circumference. For circular pitch is the circumference of the circle divided by the number of teeth. Notice it's even upside down. It's not teeth divided by circumference, it's circumference divided by teeth. And that is actually the actual distance between the teeth. And generally this is usually listed as 3.14 times the diameter over the number of teeth. I think your packet uses 3.1416, which is a little bit more accurate version of pi. And there are all sorts of formulas in here. What I think I'm going to do is I'm going to turn you loose to try some. I'm going to maybe do a couple of examples here first. I'm looking at page 250 in the metric system. Rather than using pitch in the metric system, they use module. A metric module is the distance between gear teeth in a metric gear. And M, which stands for module, is the diameter divided by the number of teeth. And of course, diameter would be in millimeters. Now you can see that's very closely related to our pitch. Pitch is actually number of teeth over diameter, it's just upside down. Yeah, that would be the pitch diameter. It would be they call it the working diameter or pitch diameter. Metric system, they don't use the term pitch, but it's the working diameter, the two diameters that are tangent to each other. I guess here in this packet they're referring to it as the pitch diameter just because they want to stay consistent. So all those formulas apply to metric gears. So now we're going to jump to page 251. We're going to do some examples here. I'm going to do number 6 just for fun. So number 6 there, circular pitch is 0.3142 inches. Number of teeth is 12. It wants us to find the pitch diameter. So if I go back to page 247, circular pitch, I've got 3 formulas I can look up. I can look up number of teeth, which we don't have a formula for the number of teeth anywhere. I can look up pitch diameter, diametric pitch, pitch diameter, and there we go. On pitch diameter, we have a formula that'll work. Morning. No problem. So on the pitch diameter there, we have D, which is our pitch diameter, which is what we're looking for, equals N, which is the number of teeth, times the circular pitch, PC, over 3.1416, over pi, basically. So we're going to take 12 times 0.3142 divided by 3.1416. Giving us 1.200. So it's a 1.2 inch pitch diameter. Make sense? So that's really the key to this, is you look at what it is you have, what you're looking for. And usually the first thing I look up is what I'm looking for. Like for number 14 there, we're given the pitch. We're given a pitch of 3.4, and we're asked to find the whole depth. So the first thing I would look for is for whole depth. See if there's anything there. Whole depth, can I find that with just the pitch? Sure I can. It says WD equals 2.157 over the pitch. So there's a formula that makes it work. Bless you. Now on Thursday, we're going to come back and we're going to look at some of these problems where you might have to go 2 or 3 formulas deep. So you may look up what it is you're looking for, and that formula may not use the information you're given. So you may have to go back and find other information to make it work. So you may have to look at what you're given and see what you can figure out based on what you're given, and then see if that will allow you to get what you are looking for. But we'll talk about that more on Thursday. Remember, tomorrow I am not here, so I'm going to kind of double you up a bit here on homework. So in the packet, page 251 through 254, problems 1 through 63, the odds. That should be enough to keep you guys out of trouble.
Gives us a lot of benefit. Underestimated.